Yes, I'd like to talk to you tonight about volcanoes. And it's a great passion of mine. And I'm a professor here at the Earth Science Department, and my specialty is anything to do with volcanoes. So I'd like to talk today about the risks and benefits of volcanoes as a natural phenomenon. And there was a children's competition in Italy a few years ago, and the children were asked to depict their idea of a volcano. And here's 3 examples from this competition. And you'll see very quickly that the idea people have about volcanoes can be dramatically different. There can be the palm tree volcano, the erupting volcano, and this must be a very junior geologist who can see inside the volcano. So you get immediately a sense that we all have different perspectives on volcanoes, and I'd like to go through some of them. And I think before I go into details, I'd like to give you a few summary points. What we talk about very frequently in volcano research is the Volcano Macrosystem. The volcano itself is just a tiny little cone at the surface. It's like the tip of an iceberg. The feeding system, the plumbing system that supplies the volcano with magma is going much, much deeper into the earth interior, into the mantle of the earth. And we must think about a large source area from which rock is rising up, and while it rises up it melts, it forms magma chambers, and there's conduits that feed the magma to the surface, and at the very end a tiny bit of this magma actually erupts. And that's what we see at the surface. Much of the magma is hidden underground. There is this concept that there is more volcanic eruptions happening as the planet gets older. And this is a tricky thing. Here is some curve that I got from a textbook. And, oops, this doesn't work so well, so I will explain it. So here's volcanoes active per year, reported volcanic eruptions. And it looks on first glance that the curve is rising up, so this is going to the 1980s. And it appears that there's more volcanic eruptions as the Earth gets older. But I highlighted in red some anomalies there. And it's intriguing, whenever we have big volcanic eruptions, more volcanic eruptions get reported in the years afterwards, because people are alert. So there's Krakatoa, 1883, and in the years after Krakatoa, people were more aware of volcanic eruptions. There's Pele, 1902, and again in the years afterwards, more volcanic eruptions were reported. The striking thing is, whenever we as a society had problems, less volcanic eruptions are reported. There we have World War I. People had other worries than volcanoes. World War II is the same, and you know, the Black Friday, the financial crash in 1929, it also resulted in less volcanoes being reported. So realistically, we have no evidence that there's more or less volcanoes erupting with time. It's a question of our attention. And here is another diagram. Oh, sorry, no, I just wanted to say it's an artifact, and here's the evidence for this. Here's a diagram of the volcanic eruptions and the intensity of volcanic eruptions from 1780 to about 2000. And as far as we can tell, there's always volcanic eruptions, and there will be volcanic eruptions in the future. On average, about 400 volcanoes erupt every year, and at any given day in the year, we have about 20 volcanoes being active. So while we speak here, some volcanoes out there, about 20, are erupting. So what I want to talk about today is some background on volcanoes. We're doing this already. I'd like to talk about direct hazards from volcanoes, also indirect hazards from volcanoes. I hope to have a little break at that point, just to stretch our legs. And then I'd like to talk a little bit about hazard mitigation. How can we prevent disasters from volcanoes? And then I'd like to close on the good sides of volcanoes. Volcanoes have a lot of positive effects for us, for our society, and I think volcanoes get a bad reputation. And I'd like to fix this a little bit tonight. So, The first part concentrates on direct effects of volcanic eruptions. We will also talk about indirect effects and the mitigation of volcanoes. Here, some images from Vesuvius in Italy, and I should point out that today the city of Naples has grown all the way to the slopes here. So this picture or this painting goes back to the late 18th century, where the population density was far lower. By now we have 5 million people living in the surroundings of this volcano. So if this would happen today, the consequences would be more severe. Here's some images from Etna and also from Hawaii. And volcanoes, they often pose a direct, an indirect, and a global hazard. I'd like to focus on the first two, the direct and the indirect one. And here I'm giving you some images of direct effects. Here, no parking, obviously. And the other image is from Etna. There's a supermarket, I think, in the background, and the lava flow is advancing. And people there trying their best to create little holes so that the lava can flow in and doesn't continue further. They're trying to stop the lava from advancing. It's not always successful, but we humans, we try our best to prevent the damage volcanoes can do. So direct hazards, they are often really in the few kilometers surrounding the volcano, and the death toll from volcanoes is just very heavily on certain parts of the planet. In particular, South America, Asia, and in Europe we have very few volcano fatalities. Not many people die from volcanoes. And there is also a difference in dangerous and not so dangerous volcanoes, and it goes back to two very eminent volcanologists, Katja and Maurice Kraft from France, and they decided that there is effectively two simple types. There's black ones and red ones. The black ones are friendly, red ones are not. So, if you know what color your volcano has, you have a good idea how dangerous it gets if it's erupting. And here is the classification. The black ones would be Icelandic type eruptions, Hawaiian type eruption, or Strombolian eruptions. And they effectively produce lava. Lava comes out at a relatively low speed. You can walk away from it if you're a fast walker. And the red ones, they are explosive. There we have a lot more energy in the eruption, and it's not so easy to walk away. It would also not be easy to drive away in some of these eruptions, because the clouds, the eruptive clouds, would be so fast they can reach several hundreds of kilometers per hour. So once you're caught up in one of those eruptions, escape is very tricky. So I'd like to start with black volcanoes. These are usually basaltic, as we call them. That means they have low silica content, and the affected areas are restricted to a few kilometers around the volcano. Up to maybe 10 or 15 kilometers possible, but usually much less than that. So Etna is a good example, Iceland I mentioned, Hawaii is another good example, and these occur locally. They can kill people, but it's very unlikely. If people are alert, if they're trained, usually we don't have many fatalities in these cases. They can, however, affect industry, infrastructure, agriculture. So they are damaging to our society as such, and we need to be aware of this. Mount Etna, for example, we have frequent eruptions there, and the land that is covered will take approximately 900 to 1,000 years before it will become soil again. So once we have a lava cover, there's no hope for us to grow anything there for quite a long time. And this can be very devastating for local economies. So here's a beautiful little lava image from Hawaii, and I'm going to show you some more images. Here we have more images from Hawaii, the no parking one I've shown before. The left one is lava from the Canary Islands, and the upper one here is from Hawaii as well. And as you see, infrastructure that cannot be moved, that's a problem. So we will lose financial investment if we're not careful about these things. Here's more images from Hawaii. Here's an aerial picture, and it shows a lava flow coming from a vent progressing down by quite a bit of distance. And here are some more local images of lava that's erupting. And you see immediately, they come out as little tongues, or little, lobes, if you will. Here's a lava vent from Hawaii. So this is where the lava extrudes. There's a person for scale on your left. And this is quite a large lava vent. And here we have a little bit of a skin on top of it. And here's an outlet. So here it drains into a lava flow that will then run downhill and potentially cause the parking problem I showed you a minute ago. Here's a lava lake. And there's a bit of bubbles coming up in the lava lake. And therefore we get some small fountains. And lava lakes effectively form if there's a hole in the ground, like a crater, and lava flows in and it fills it up. Then this is what we get, a hole filled with lava. Once this solidifies, it makes a crust, and often we build these beautiful columns in solidified lava. This is what we see here from top. You see the polygonal shapes, and once this would be cool and we cut into it, we would see many, many pillars or columns, like you might have heard from the Giant's Causeway or so. So this is this phenomenon from cooling lava. Another type of lava that's less pleasant to work with and less pleasant to walk on is called AA lava. AA is a Polynesian term from Hawaii, and it means a very rugged surface. This is what we call a block lava, and it moves a bit like a caterpillar. So it moves forward, not like the tongues for the lava I've just shown you, the fluid lava. This is more sticky, and it will affect things in its surrounding. It will burn vegetation, and if your house is in the way, then your house will be affected as well, obviously. So here I've given you one of these caterpillars, and this is how the lava moves, like the chain on a caterpillar. It rolls over this lava, and it's not very fast, but once you're in front of it and you cannot move, you have a problem. So this is damaging to non-movable objects. This has been a problem to Europe as well. Here's some images from Vesuvius. This goes back to the 18th century. And there you see a large lava flow coming down from the actual cone, moving down into the agricultural fields on the slope of the volcano. And these two houses were, I guess, lucky, but maybe some others were not. Maybe this one here. So I think you get the idea. And here's another image of the same thing. This is just a different perspective. Here we have lava coming down again from Vesuvius, and it will affect the surrounding of the volcano. So ideally, you don't build too close to a volcano that's erupting very frequently. So here is the situation from Etna. I showed this image earlier, and here's a little tourist center, and I think the lava stopped it. It did not destroy the tourist center, but it got very close. So here, human efforts are often insignificant because we cannot stop volcanic eruptions. It's just impossible. We can try to divert the lava, we can try to create holes for it to flow into, but stopping it, as far as I understand, it's impossible. So, black volcanoes are usually not very dangerous apart for infrastructure, but there's exceptions. You might have heard about the Laki eruption in 1783. That was a long fissure eruption, and you see the vents here on Iceland. And this eruption produced a gas cloud that moved towards Europe. And this caused a lot of fatalities. There was a famine afterwards in Iceland itself, and it's believed that some 27,000 people were dying, not as a direct consequence, but as an indirect consequence, because the animals didn't have any grazing material. They got sick from eating the poisoned grass. The people didn't have any milk, any meat, and the consequences were severe. It's also affecting the United Kingdom, and in fact the church records in Skåne are pretty clear that the death rate in the years after the eruption was higher than usual. And it's likely because the poisonous cloud was also depositing fluoride and other elements in those areas. So there's good evidence that these eruptions can be serious, and if that would happen today, we would still be affected. Another eruption that some of you might remember from the days, I was only 2 years old at that time, but there was the Jemez eruption on Iceland in 1973, and this was on the island of Vestmannaeyjar, and there a little volcano started to erupt, and it started to fill in the harbor. So here's the vent site, here's the lava flows, here's the settlement of Jemez, and you see the harbor area. And the Icelandic people were very keen to stop the lava from filling in the harbor, and they brought in the fire brigade to put water on the lava to cool it down. It did have some effect, but some of the harbor entrance got narrower, but it didn't close completely, so it's still usable today. So here's some impressions from the 1973 eruption. There was only one person that died in that eruption, and this was a strange case. This was somebody who got lost, and he felt he needs to get something from a house, but he couldn't find the right place anymore, and eventually he got into a house, and then there was gas in the house. And he must have bent down or so and inhaled too much gas, and he didn't get up again. But it was not a direct consequence of the lava. So these black volcanoes often make shields, and the shields can be of different size. There's Icelandic shields, there's the Hawaiian one, and there's the biggest volcano we have, at least in our solar system that we're aware of. That's Olympus Mons on Mars, and that's likely of the same type. Olympus Mons is a huge volcano. It's 340 miles across, and it's very tall, and here's an image from it. It's got a surface caldera, and to our knowledge, it's the largest volcano recorded. There may be other ones we haven't seen. We cannot see all the surfaces of all the planets in the solar system, but this one we have observed. So this is the concept of black volcanoes, and I'd like to close that here. Here's again a little summary: Icelandic, Strombolian, Hawaiian types, and Volcanian ones. And apart from immovable objects, they're not so dangerous. There is one exception again, and that is if the magma gets in contact with water, then it gets a bit explosive. It's like if you sprinkle water on a hot plate, it might burst out. So this is what happens here. It goes back to the emergence of Surtsey in 1965. There, a volcanic vent started to erupt under the water, and it grew larger and larger until it reached the surface. And here you have water inside the vent, and the interaction of magma and water can lead to the conversion of water to steam. And when it does so, it will increase in volume, and that's causing the eruption or the explosion. When water gets converted to steam, the volume increases factor 1,000. And if you have a confined space, this will lead to an explosion. So here's a few impressions from back in 1965 when the island of Surtsey emerged, and the island is still there. Not all islands that emerge will make it. Some of them will be eroded again, but Surtsey is still there, but it's getting smaller every year. And some people say if there's no new eruption, it'll be gone in 50 or 100 years. So the next topic I'd like to delve in is explosive eruptions, and they are a lot more serious. So magma contains volatiles, gases, and these gases are usually dissolved. It's like fizzy water, sparkling water in a bottle. As long as it's under pressure, you only see the water from the outside. Once you might shake it a little and you open it, you depressurize the water, and all the bubbles come out. And if you have shaken it too much, it'll spurt out. It's actually a mini explosion. And that's how it works in volcanoes as well. The gas is very, very important. If you have too much gas in the system, it will drive the volcano towards high explosivity. And if you shake it with earthquakes, it doesn't help, it makes it worse. So here, if your magma has a lot of gas, chances explosive eruptions can happen. And if you have magma that's high in silica content, by the development of magma, it tends to have more gas than basaltic magma that makes the black volcanoes. So these guys they throw particles up in the air, there they get in contact with air, they oxidize, and they often make red ash. That's why they're called red volcanoes. And these are the dangerous ones. So if we have magma rising up, the gas bubbles will grow, and at some point they will rip the magma into tiny little fragments at this fragmentation level, and this will make small particles and ash. And therefore we get big eruptions with ash columns and all these kinds of things. So explosive eruptions work differently to these lava eruptions. Usually what we call the magma then is high silica or a rhyolitic magma, and the more silica the magma has, usually the bigger the eruptions and the bigger the explosions. So, as I said, this is due to the gas, and high silica also means high viscosity. It means the magma has a high resistance towards flowing. It doesn't want to move, and the gas bubbles will cause it to fragment because they cannot escape. So, this will cause big eruptions, and here is a pyroclastic flow from Merapi volcano in Indonesia, and you see it's large and voluminous, and it travels down very, very fast. So if you're in the way of that, it's not a good sign. So red volcanoes, they are the greatest risk, the greatest direct risk. They cause pyroclastic flows, ash falls. They also sometimes produce lateral blasts, meaning directed surges and blasts to one side of the volcano. And they have often also very negative indirect effects. Lahars, mud flows that is, flooding, and tsunami can happen with this as well. So here we are focused mainly on Indonesia, the Caribbean, and Northwest America, the Andes, and these volcanoes all tend to be more explosive as opposed to, say, Hawaii or Iceland. So the different types of volcanic eruptions, they have different hazard potential, and there's a big contrast. So you want to know whether your volcano is red or black before you move there. So red volcanoes, they will erupt like this. There's Plinian type after Pliny, who described the eruption of Vesuvius in 79 AD. There's Vesuvian type, which was also a form of eruption seen at Vesuvius. And there's the Pelean type, going back to the 1902 eruption of Pele in Martinique. And I'm going to run you now through different types of eruptive processes. And here I'd like to start with Ashfall. This is an image of Mount St. Helens in 1980, and you see the material is pumped out. Huge amounts of gas and ash are produced there. And this is often what we term a Plinian eruption, meaning a large column that goes up several kilometers and spreads out. And then the ash might fall down, and it will cause a blanket of ash. Thicker close to the volcano, thinner further away. The ash can be very devastating for humans. There's often people who have breathing problems when there's ash fall, and of course they will also be very much devastating for a lot of our infrastructure. So here's a few more images from 1980, Mount St. Helens. So here it looks like that it's a grey day, but it's actually ash in the air. And here, this is not snow, this is volcanic ash on these cars. And cars are not really good in these conditions because you need to have air. There's an air filter system in your car, and if this clogs up, then your car cannot operate. So under ashfall conditions, many of our usual tools, our technical aids are not working particularly well. And here is a quote from Lord Byron, who wrote this down, which was 1815 after the eruption of Tambora in Southeast Asia. And he says, "The bright sun was extinguished, morn came and went, and came and brought no day." If we have too much ash, we're losing the sun. And this, of course, can be bearable for a short time, but if this ash is in the system, in the atmosphere for longer, it's problematic. It can reduce the heating effect from the sun, and we get processes like volcanic winters, and they are not very good for us. So here are a few more impressions from Mount St. Helens. This is the ash cloud erupted from the volcano, and it affected quite a large area. So here a little bit more. This car down here is still operational, but you see the cloud it produces just from secondary mobilization of the ash. And once we have rain on top of this, the ash becomes mud, and we get mud flows. And they will move downhill, they will fill depressions, and this can also be very disturbing for infrastructure and other activities. Here's a little map of the ash cloud from Mount St. Helens. Mount St. Helens is here on the left. At 9:15 in the morning, it was affecting maybe an area 100 kilometers away. And by afternoon of the same day, it moved for hundreds of kilometers all the way down here. And all of this area was affected with ashfall. But of course, closer to the volcano, the ash would be thicker than further away. The ash usually forms a blanket, or tephra is another word for volcanic particle, and it forms a blanket irrespective of topography. We will talk about pyroclastic flows in a minute as well, and they often center towards low ground. They will deposit more material in depressions, while ash often makes a blanket of an entire terrain, and then it might be washed into depressions from secondary processes like rainfall. So pyroclastic flows, they are the real dangerous phenomena at explosive volcanoes. So if you have a red volcano and it's rumbling, this is what you really need to watch out for. The eminent scientists, like you cited earlier, Katria and Maurice Graf, they died in one of those pyroclastic flows in 1990 at Unzen volcano in Japan. And this is really the biggest killer in terms of direct volcanic effects. I showed this image before, Merapi, Indonesia. Here is a valley fill from Augustine volcano in Alaska, and you see some people there on the slope of this valley. And the valley, the lower material there, that's all from the ashfall, ash as well as bigger blocks that have been produced by the volcano. So let me give you a sense of how this looks. This is Pinatubo, 1991. I understand this car did not make it. So here we have Pele 1902, and this was taken from by a scientist, Laki was his name, and he observed this in August of that year. He came after the city of Saint-Pierre had already been destroyed, so this was one of the later pyroclastic flows. It was not the one that devastated the city, and he only observed it from a distance. But this was one of the first images of a real pyroclastic flow. And you get the idea that this is so overwhelming that we have really nothing to put it against. A short word about this eruption, 1902, Pele. It was one of the eye-opening eruptions of the last century. It was the most devastating one in terms of human life. And people didn't really understand volcanoes to the degree we understand it today. People tried to evacuate the city, but the mayor, he instructed people to stay because there was an election coming up and he didn't want people to leave. It could have upset the whole system. There was a candidate that seemed to get a lot of support, whom he didn't like, so he encouraged people to stay instead of leave. And even when the ash started to fall, he was still not positive about this. And yeah, the consequence was that the city of Saint-Pierre, down here, only about 6 kilometers from the volcano away, was completely wiped out. 28,000 people died within minutes. There was one survivor only. He was in prison. It's not quite clear whether he was a murderer or not. At least he was accused of being a murderer. He was a thief, actually, I understand, and he got into a quarrel about some loot with some other thief, and one of them died. So he was put into prison, into a really bad dungeon cell with very poor ventilation, and that was his lucky strike. So he became a circus star afterwards in America as the man who can withstand the volcano. But I read that apparently he died a poor man, so I don't think he got very happy about the whole thing anyway. So, Montagna Pele, 1902, it was a beautiful city, the pearl of the Lesser Antilles, Warning signals were ignored at the time. The town was wiped out within minutes. A hot surge of ash rushed through the town. It was about 400 degrees hot, we estimate. 28,000 people died almost instantaneously. And another problem was that there was a lot of rum distilleries around the town, and they all started to burn. And a lot of rum was kind of flowing down into the city center, and rum is not compatible with fire in the sense that, of course, it all flamed up, and the city burned for many days afterwards, causing extra damage to the infrastructure, leaving the city entirely destroyed. So, one of the important eruptions that belongs to this type, this pyroclastic type, as well as the Mount St. Helens eruption in 1918. 1980. I showed some images a minute ago for Ashfall, but it also produced the pyroclastic flow. And here you see Mount St. Helens just before the eruption. And what happened really is that the magma pushed against the volcano flank became unstable, it was rushing down, and it uncorked the volcano. And as a consequence, the big eruption started. So here, we're seeing the volcano where this side of the flank of it is just falling down, and the first eruptive material is starting to come out. And here, we're seeing the eruption really going strong. And eventually, it led to the big eruption that we all know of. Here's a postcard that I bought in the US a little while ago, and there is a drawing of the volcano prior to 1980 and the volcano today. As you see, much of it is gone, and all of this material would have been thrown away by this massive explosion. And there's a new dome growing inside the volcano right now, so the volcano is regrowing. But it'll take probably several generations before it reaches its proper size again. The area was evacuated in time, not many casualties, but 2 volcanologists died, and these are 2 of the volcano heroes. They were stationed there to observe the volcano, and they didn't get out in time. Here we see a lot of the trees in the area, it's a very forested area, were fallen over, and it was damaging for the forestry in the area, but it was good for volcanology, because the trees, they gave us a direction of how the ash moved. And this was very, very useful because it allowed to reconstruct exactly what happened. Here's a map, and all of these arrows of how the pyroclastic flow moved comes dominantly from the trees that were fallen over. While it was damaging to the infrastructure, it was a great leap for our understanding of how these things work, and it allows us to make estimates of the direct area that's affected by those eruptions. And as you see, the flank of the volcano that collapsed here gave rise to eruptions in these directions. This side of the volcano was rather safe. As I mentioned, there's a new dome growing, and here it is. This is the new dome. It's coming out like toothpaste, and it's very slow growing. It's hot, but people can go there. The American geologists have been flying there with a helicopter and tried to get close and take samples and all that. It's possible. And it's a slow process, as I said. It'll take many tens of years, if not hundreds of years, until the volcano has reached its former size. But then, likely, it will erupt again. So the life cycle of a volcano is different to a human life cycle, but they have life cycles after all. Another example I'd like to delve in is Merapi volcano. I mentioned him before, sitting in central Java. Indonesia is spiked with active volcanoes. It's about 130 of them. Each of these little yellow dots is an active volcano. And Merapi sits right here in central Java, next to the city of Yogyakarta, with about 3 million people. So here's Merapi on a calm day. And several cultural monuments are in the area, and many of them were actually abandoned and covered with ash and pyroclastic material. And people didn't understand this for a while until we witnessed the 2006 eruption of Merapi. And there was a little village called Kaliatem. It was about 6 or 7 kilometers away from the volcano. And I don't know what this thing is there, but well, we have to live with it, I'm afraid, this little box there. But anyway, here's some impression from 2006 in Kaliatem village next to Merapi. And yeah, you get a sense of how little villages can be entirely buried. You get a sense of how Pompeii, for example, in Italy, was buried by pyroclastic flows to a point that it was actually forgotten that it ever existed. It was only rediscovered in the 19th century that there was actually a town under the ash deposit from these pyroclastic flows. So this is a really severe effect, and in this particular eruption the village was also evacuated, but again 2 people died, and they were geologists that were stationed there to observe the volcano. So being a volcanologist at red volcanoes is dangerous. So here's a few more impressions, and this is actually the observation bunker. So the 2 volcanologists were in there, and the bunker was covered. So I don't think it was very pleasant in there. They didn't actually get directly affected, but they were indirectly affected. They were buried alive, unfortunately. So these pyroclastic flows, they can take different forms. The Plinian eruption with a high column. Then we have a boil over situation where it's a bit like a pot of water that boils over. And then we have the blast. This is, for example, when one side of the volcano gets unstable, as we've seen for Mount St. Helens. And these are the main types of explosive eruptive deposits. If you've ever been to the Canary Islands on holiday, on Tenerife, for example, you see that these deposits are widespread there. And, as I said earlier, they fill topographic depressions. And here you see a channel or a former valley in the hillside, and it's been completely filled with these light-colored pyroclastic materials, very pumice-rich. And, well, we must assume that life on the island would have been wiped out by these eruptions because they were very large, and indeed there is fossils in some of these deposits. This is the giant canary rat. It was about this size, and it's believed that it is no longer there. It's extinct, partly from eruptions and partly because the local Aboriginal people, they like this for dinner. So the rat isn't existing anymore, but we have fossil bones from it, from these pyroclastic deposits. So I'd like to talk a little bit about indirect effects, and here they can be very dramatic as well, and they can cause a lot of disruption and also loss of life. And one of the major phenomena here is mud flows, lahars, that's an Indonesian term. Lahars, they form when volcanic material mixes with water, like volcanic ash. It can be rainwater, it can also be meltwater from snow and things like that. And we get these fast-moving mud flows. They have the runniness of water, but they have the density of concrete. And if you're hit by a wall of water that's got the density of concrete, it will be damaging. So rivers of mud are reported in these situations. The most pronounced example that I'm aware of, the most serious one, is Nevada del Ruiz in Colombia. And here we had hot ash that mixed with snow, and it traveled downhill for about 70 kilometers. And there was the city of Amero, and yeah, this is where the mud flow came down. Here was the city, and the city got completely entrenched in this mud, causing something like 20,000 people to die, and most of the city was severely devastated. Here's some impressions from the city, all drowned in mud. The big drama about the Amero event was that the USGS, the US Geological Survey, had worked there a few years before, and they made a prediction, and they said the area in orange is a danger, and the areas in brown are likely going to be affected by mud flows. And they identified that the city of Amero is right in the middle of this. But the mayor of Amero, he wasn't very interested in this. So it didn't fit his overall policies, so he ignored these things. And when the eruption happened, this is the lower map, of course the city got wiped out. So the drama here is that we could have prevented this, but we failed to do so because of other interests. Another example, which likely could have not prevented, but this is an example from New Zealand. The volcano of Ruapeo had a little eruption, and there was also a little breakage in the crater lake, and the water of the crater lake washed down the hillside and created a mud flow, and the mud flow took out a railway bridge, and a train came. And this was the big express from Auckland to Wellington, and the bridge was gone. And 151 people died. It's a national monument in New Zealand. If you ever get to the North Island of New Zealand, you can visit it. So there is the monument that's reminding people of this disaster. The bridge was actually not very high, but well, the train could obviously not make it over. And here's some impressions of how the situation looked back then. So here's Ruapeo Crater Lake, and you can see the water in there. You can get the idea that this can spill over and wash down. Here's an image of Ruapeo from a distance, and here is the disaster monument that I visited a few years ago when I had a chance to go there. The tragic side is that if you look at the rock record, and back in the 1950s people were likely not aware, but if you look at the rock record in the area, there is loads of deposits that come from lahars. This was my Hayakar at the time, so for scale. And look at the big boulders and the mud matrix. So the area is affected by these kind of events, and nowadays people know. So they are trying to stay clear of this. Another aspect that I think is important is tsunami. There's different types of tsunami. There's tsunami that come from earthquakes, and there's tsunami that come from volcanic eruptions. And tsunami is a Japanese word, and Japan was very frequently affected by tsunami that come from the Pacific, partly from Hawaii, but also from earthquakes out in the Pacific. And the Fukushima event was a tsunami, likely not by a volcano, but by an earthquake. And it affects these low-lying areas in places like Japan. These waves can be very large, and there is not much we can do about them apart from stay clear of it. And one of the most disastrous tsunami I'm aware of is the one from Krakatoa in 1883 in the Sunda Strait. And the volcanic eruption wasn't very nice, but the tsunami was really critical. And it's believed that it wiped out something like 300 villages, killing something like 36,000 people. So here's some images from Krakatoa. This is Ana Krakatoa, the new volcano growing inside the Krakatoa complex. And there is this story about this little ship, the Beru. It was a Dutch ship. It was the Dutch East Indies back then. And it's been reported that the ship has been seen to be picked up by the tsunami, and it's been moved for something like almost 2 kilometers inland. So the power of the tsunami was so big that the whole ship has been moved on the wave for several kilometers and was dumped in the jungle. You can still go there today. You will still find a bit of metal. I also understand, I read some article that says that there's a monkey colony now living around this, but it's a monument for the enormous force of tsunami waves. So this is something to give you an idea. So if people today are still worried about tsunami, there is good reason for that. This is Krakatoa in the Sunda Strait, and the dark brown area, these areas here, that was all the areas that were devastated by the tsunami. And here's travel speeds in minutes, and within an hour or so, the tsunami was through the Sunda Strait and affected all these areas. And Jakarta, the present-day capital of Indonesia, is sitting here. And about 2 hours or so after the big eruption occurred, the wave reached Jakarta, and it's been demonstrated in, for example, the harbor records that the wave arrived, and this allows us to calculate this travel speed. So it's a very fast thing. You might have heard about these views that some of the Canary Islands might collapse and produce tsunami. Indeed, there has been all sorts of speculations about particularly the island of La Palma that might collapse and produce a huge tsunami. Some people argue this tsunami might be so big that it will travel across the Atlantic all the way to America. It might destroy the eastern seaboard of America. Some people argue it might then bounce back and come towards Europe again, and then Ireland, the UK, and Norway might be most seriously affected. Personally, I think that's overdoing it. But who knows? I will actually go to La Palma in 6 weeks, and I will have a close look at the situation. But the good news is people have realized the danger, and the Spanish colleagues have put instruments there, GPS instruments, and they measure exactly whether anything in the volcano is moving. And the good news is that despite various eruptions, the flank has not moved in the last 20 years. So we understand it is reasonably stable. So here is this flank, this unstable flank. It's this steep part here. And the argument is if this slides into the sea, we will get this big tsunami. La Palma Island had historic eruptions in 1585, in 1677, in 1712, etc. None of them really caused a mega tsunami or this kind of thing. The 1949 eruption produced a crack on this hillside, and the offset was about 4 meters. And this got people really concerned. But the good news is nothing moved in the 1971 eruption. So we would have expected that if this was a serious problem, a new eruption would cause some damage, but it didn't. So here's some calculations which some of the geo colleagues did, and I am a bit skeptical. It's a numerical model on a computer, and the computer does what you tell it to do. It doesn't necessarily mean it's real. So here's some estimates. If the island of La Palma collapses and erupts, then the wave might spread out. And here's the predictions they come up with for Florida, for example, suggesting that the wave, after a certain travel time, might reach the western seaboard of the USA and cause serious damage there. We don't know whether it's true. It could be, but it could also be that these flanks of big volcanoes come down in small bits, and then there is no big wave to be expected. So we will have to wait and learn. But let's have a short break now, and I'd say let's stretch our legs for 10 minutes. I have some material outside if you're interested, and afterwards I will tell you a little bit about what we do to monitor volcanoes and the good side of volcanoes as well. Thank you.